Caltech. It's my pleasure to introduce Dr. Aram from Caltech. Aram is from MIT and is currently a Burke Fellow at Caltech. His research explores the limitations of quantum algorithms, drawing on the ideas from statistical physics and quantum foundation theories. Today, I will speak to talk about his work, when to use quantum algorithm. This is a topic that sits at the heart of understanding both the power and the limitations of quantum computing. Please join me in welcoming Eric.
Thanks, guys. That was a very nice introduction. So yeah, I'm Eric. I'm a Burke Fellow at Caltech right now. And today I'll be telling you some ideas that I've developed in quantum complexity theory, really trying to nail down the answer to this question of when we should think to use quantum algorithms. We're in a very exciting moment in quantum computation. Quantum computers are being built and able to do very non-trivial things. And today I'm going to kind of lay out the state of the art of what's going on in this field of research and where quantum algorithms really show a lot of promise and where they don't. So before I get into all of that, I really should begin by telling y'all, what is a quantum computer? You know, this isn't necessarily a quantum audience, and to even take a step further back, I really should be telling you what a computer is. Hopefully, you know, it's a computer science department. We kind of have an idea of what a computer is, but you'd be surprised. So anyways, okay, what should we think of as a computer? Well, in kind of our standard model of computation, you know, you can think of being some end user. You're trying to type some input to some program or whatever. So you type some bit string or you type some ASCII that gets turned into bit strings. And then your computer reads it in, and then it runs some subroutines, right? So the internal state of kind of the computation that's going on is going to be represented by some bit string. This is, you know, you can think of as the bits in your RAM or whatever, kind of telling the computer what the internal state of it is. And you might run some sequence of subroutines that take these states to other states. And at the very end, we get some answer that as the end user, we're very happy with. Or maybe we had some bug and we, you know, changed some of these subroutines. But at a high level, this is sort of our model of computation. Now, as you know, I come from a physics background, actually. And the very physics question to ask here is, well, why is this natural? Like, why should this be the model of computation we use in our theorems and are interested in? Well, someone in the 80s actually thought of this question as well, Ravan Gandhi. And he had a very nice paper where he essentially showed that this standard model of computation, so for the more experts in the room, what we would call Turing machines, are essentially polynomially equivalent to Newtonian physics, I'll say. So what I mean by this is, what Turing machines can compute is exactly up to, you know, what they can compute efficiently is exactly what you can compute using some kind of physics experiment. So in other words, every Turing machine, or you can implement a Turing machine using kind of some Rube Goldberg apparatus or a Charles Babbage analytic engine, kind of obeying the laws of Newtonian physics. And also any Newtonian physics experiment you can simulate efficiently using a Turing machine. So these two models of computation, if you will, are essentially equivalent. Now, okay, I don't know if people have been keeping up with the literature since the 1600s, but physics has progressed a lot since Newton. So you just have to look at, you know, his cause of death and his Wikipedia page of trying to turn mercury into gold to realize we kind of progressed in science since then. And actually, physics as we know it isn't described by what we would call Newtonian physics, but instead it's described by what we would call quantum mechanics. So I'm not going to teach you all quantum mechanics in an hour, but what I will tell you are some implications of quantum mechanics. So for one, it turns out quantum mechanics is very difficult to simulate. So in other words, or just to give an example of this, last year, Google had some problems, some physics simulation they wanted to perform on a pretty small system. So it's some system of 65, you know, electrons, let's say. obeying the laws of quantum mechanics. And they estimated how long it would take to perform this computation on the frontier supercomputers. So this is like the third largest supercomputer in the world. It's at Oak Ridge National Labs. It's very expensive to run anything on it. And they estimated that computing this property that they were interested in would take over 3 years on this supercomputing cluster. So, and this is if you had access to the whole cluster, which in practice you don't. And God forbid you have a bug and you have to rerun this 3-year computation. There goes your PhD. But at any rate, in principle, you can simulate these systems on these large supercomputing clusters, but it gets very expensive very quickly. So this was actually also realized back in the 80s. And the physicist David Deutsch realized that actually the Turing machine isn't really the right model of computation that's equivalent to physics as we know it. And really, what it is what we now call quantum computers. And it turns out this is polynomially equivalent in the sense of any physical experiment you can conceive, you can simulate efficiently using this model of computation. Okay. Now, again, I'm not going to teach you the intricacies of quantum computation, but just at a high level to kind of understand how powerful it is, we can go back to this 65 particle system that Google was interested in. And they actually developed a quantum computer, their Willow quantum computer, as they call it. I don't know why their press release has it lying on a beach, but at any rate, this is their press release image. And they actually computed this property they were interested in, and it only took them 2 hours to do this. Yeah, exactly. So it's on the beach. They're trying to advertise for new hires or something, but it makes for a funny slide. At any rate, it's much, you can kind of estimate it's like 13,000 times faster running it on their very primitive quantum computer in the grand scheme of things. Quantum computing is a very new field, and compared with the frontier supercomputer, which is huge and expensive and everything. So, okay, I've been kind of beating around the bush. I haven't really told you what a quantum computer is. Again, I'm not going to get into the nitty-gritty details, but just to give a high-level picture of where this power is coming from. So we can go back to kind of our model of computation. All I've done here is I've put a little atomic icon there to indicate it's a quantum computer. But just like a normal computation, you just input some bit stream input to your program. And then if you've heard anything about quantum mechanics, you might have heard that it's probabilistic. So your first guess as to how a quantum computer works is, oh, maybe it's just some kind of probabilistic computer. So in other words, it's sampling from some probability distribution of internal configurations instead of having one definite internal configuration. And it actually turns out quantum computers are even more interesting and powerful than this. And actually what quantum mechanics tells us is that the internal state of our system you can represent using kind of a signed probability distribution. So I won't get into the details, but this is some more general kind of internal state than what a Turing machine or even a probabilistic Turing machine would give us. And our goal as a quantum algorithms researcher or designer is to design kind of these signed probability distributions to interfere in a way that you're sampling from a distribution in the end that's centered on the answer you're actually interested in. So it's not trivial at all to design algorithms capable of doing this, but people do this daily now. And just for concreteness in the rest of my talk, I'm going to call this object the quantum state. Just like for a Turing machine, this is the internal state of a Turing machine. This quantum state is like the internal state of a quantum computer. So I'm going to call this a quantum state. Okay, so what? This is some new model of computation. Well, as I kind of alluded to earlier, there are some simulation problems that are really interesting to physicists that you can actually come up with quantum algorithms. So algorithms that run on these quantum computers very efficiently that can simulate these systems that we don't really know how to efficiently simulate using kind of traditional algorithms. But actually, it's more than this. So problems kind of beyond physics, things like factoring or discrete log, unstructured search, inverting large matrices, these problems, or solving these problems, become much more efficient using quantum algorithms compared to kind of traditional algorithms in this Turing machine model of computation. And once you start saying things like linear algebra is exponentially more efficient, the VCs get involved. So now you have startups, raising ludicrous amounts of money. You get Yahoo Finance articles that say crazy things like quantum computing will be the biggest theme in AI in 2025. Well, we're in 2026, and I think we can safely say this prediction didn't come true. And then you get even crazier things, that have many things wrong with them, like quantum computing achieving the singularity in 2025, a ChatGPT moment. There's so many issues with that statement, but okay. Obviously there's a lot of hype is what I'm trying to get across to y'all. And part of the reason there's so much hype is because we're kind of in this weird early stage of quantum computation where we have some kind of small scale proof of principle experiments and computations that we're running on these things, but we don't have access to very large quantum computers. And without these very large quantum computers, these heuristics and things we develop, we can't really test them. So it's very different from the current state of normal, traditional computation. And we really need new tools to understand the limitations of quantum algorithms, to kind of understand, well, where are quantum algorithms going to be successful? And that's what I do in my research. So maybe just to move here, I look at problems, particularly in learning, optimization, and sampling, and I try to understand, well, how powerful are quantum algorithms in these kinds of meta tasks? And so maybe to nail this down more specifically, if I'm given some problem, I'm interested not only for quantum algorithms, but also classical kind of traditional algorithms. Well, is this problem hard? If this problem is easy in our normal model of computation, there's no reason to spend billions of dollars on quantum computers. You can just run it on your laptop. So, trying to understand the complexity of problems is something I'm interested in. Also understanding kind of the structural properties that make problems hard. If we understand why a problem is hard, and this is often something complexity theory doesn't really tell you, but if we can understand why a problem is hard, then we can consider the easy instances of these problems and design algorithms that take advantage of this knowledge we've gained in the course of doing this research. So in this talk, I'm going to tell you about what the state of the field is in two settings, essentially. First, I'm going to talk about learning, so using quantum algorithms for machine learning. And then I'm going to tell you about optimization. And you'll see in the course of this talk, I have some very pessimistic results over here on the left, but the story in optimization is really rich and very interesting in where quantum algorithms might be useful. So, okay, let me just start by talking about learning. And to motivate this, I'm actually going to go back to the original motivation of quantum computers. So it's the fact that quantum computers are essentially equivalent to any physical process. So any physical process that happens in not so long a time, we can simulate efficiently using a quantum computer. So where does this come up in practice? Well, a typical setting is what people call drug discovery. So this is something that pharmaceutical companies are interested in. And the typical setting is something like this. We have some biological process. I don't know biology, so I'm just using shapes. But you might have some enzyme binding with a protein, and then you don't want this to happen in the body. But to understand why it's happening, you really need to understand kind of the quantum mechanics of these molecules, because it's a very small scale physical process. And often in drug discovery, this is some process we want to inhibit. We want to design some molecule that we can introduce to the bloodstream or whatever that stops this process. So again, we want to kind of learn the right thing to put here to optimally stop this process from going on. And so as I'm kind of using loaded language here, the way we do this already is essentially machine learning. So this won the Nobel Prize in chemistry a couple years ago. People have been interested in using AI and things like this for essentially predicting the outcome of what will happen if I introduce a molecule, via a drug or whatever. But part of the issue is, like I mentioned earlier, quantum chemistry or quantum mechanics is very difficult to simulate. So we don't expect even like a very powerful machine learning model to actually compute what's going on here. In the end, what's going on is your machine learning model is really just guessing kind of the outcome of this process. So if you were to actually do this, you would then have to pay a chemist to go into the lab and actually test, if your model was hallucinating or not. And so it's great and it's very powerful and kind of whittling down the search space of what molecules we should be interested in for developing drugs or whatever. But there's still kind of this, guess and check nature to this, just due to the fact that quantum mechanics is really hard to simulate. So to get around this, I'm going to tell you an idea that was very influential like 5-10 years ago, which I'll just call the quantum learning strategy. So here, what you do is you parameterize some description of this molecule that you're interested in. So, what atoms are going to be in your molecule, how far they're spaced or their arrangement. And then, like I mentioned earlier, quantum computers are very good at simulating quantum mechanical processes. So we can actually just simulate this quantum chemistry that's going on a quantum computer. And then we train the model. So we optimize these parameters to kind of maximally inhibit this process. And like I mentioned, this was a very influential idea. Lots of papers, lots of review papers were kind of developed along these lines. But like I mentioned earlier, we don't have large quantum computers today to kind of understand the scaling of this heuristic. In the end, you have to kind of train this model, and it's not necessarily true that this model trains efficiently. And so you can ask, does this work? And in a series of papers, I showed that unfortunately, no, it doesn't work. So let's try and understand why. Well, to do that, first I'm going to tell you very quickly how neural networks learn. So not even quantum at all at this stage. And to give it an operational meaning, if you're trying to optimize some neural network in time for the next conference, you're optimizing some function over 100 billion parameters. And it's not obvious at all that this should succeed within the lifetime of the universe, let alone in 2 months or whatever for neurons. So it's a miracle that this works, but we actually sort of understand why it works. And to illustrate why, let me first introduce a feed-forward neural network. So if you're not familiar with these kinds of diagrams, just at a high level, what's going on here is, I have my machine learning model. Once again, I have some input that goes into this model. And then you can view a feed-forward neural network as a series of subroutines or functions being applied to these bit streams that transform them in some way that lead to some output. And you kind of initially are just guessing what these functions should be. And unless you're a very good guesser, you're not going to guess the right thing. So you'll get some garbage out. But then what you do is you just introduce some supplementary algorithm, which changes these functions using something like gradient descent or some training algorithm. And then you make these subroutines work very well, and then you get some good output at the end. And you can show actually, I'm skipping many steps, obviously, that essentially this optimization procedure is essentially equivalent to trying to find the minimum of a random polynomial. So you can view roughly this randomness as coming from nonlinearities in your network. And the degree of the polynomial kind of goes as your depth. But if you're not an expert, that's OK. This is just some polynomial that it turns out if we can optimize polynomials that look like this, we can train neural networks efficiently. And actually, it turns out that these kinds of polynomials are efficient to optimize using what are called second-order optimization methods. So if you're familiar with things like Newton's method or BFGS, these are second-order optimization methods. Atom, if you're familiar with that, that's what people use in practice. This is like an approximate second order method. And the reason really is that our loss landscape, so this function, all of its local optima are near the global optimum. And it might have some saddle points kind of higher up in the landscape. But that's why if you have a second order method, you can get through these index or saddle points. Okay. So now we can ask, well, what about quantum networks? Well, I should tell you what a quantum network is. And here it's roughly the same idea, except now, like I kind of alluded to earlier, these internal states are these strange quantum states. So now the internal state at each of these layers, instead of being some bit string or a vector, are now these quantum states. And just like in normal neural network, generally, if you just guess what these transformations should be, you're going to get some garbage out. And the hope is that you can introduce, once again, some second optimization algorithm to kind of tune these functions to get the output you want out of the network. And the question is, well, does this work efficiently? And okay, I proved theorems that essentially say that quantum networks generally don't have this nice polynomial description. And in practice, if you look at the loss landscapes of these quantum neural networks, essentially you have to optimize a function that looks like this. And if you're familiar with methods like gradient descent or Aram, you'll know that if you start from a random point in this optimization landscape, these terrible local optima, you'll just get stuck in. And so unless you're starting kind of exponentially many times, you're going to end up in one of these terrible local optima and not optimize this function efficiently. So yeah, just for reference, this is what the kind of traditional feed-forward neural network looks like. And I don't have time to get to the proof, unfortunately, but really this proof of this kind of loss landscape comes from ideas in statistical physics. So feel free to ask me after if you're interested. But okay, at any rate, it turns out this is kind of true generically. There are some tricks to get around them that were also kind of influential for the last 5-10 years, but it turns out actually in these cases, you can come up with classical algorithms, so algorithms that run on your laptop, that efficiently simulate kinds of these tricks to get around this negative result. So again, unfortunately, I don't have time to get into this really, but I just wanted to lay out what I would call the quantum learning landscape, or the landscape of the field. So what the series of results essentially showed, okay, well, first, this is kind of what these very optimistic headlines in Yahoo Finance are kind of hoping for, are results that there are learning problems which are both classically hard and quantumly easy. So hard for kind of traditional neural networks, but easy for quantum neural networks. But what this line of results shows is that either you're kind of in this classically easy setting where it's not super interesting, or you're in this quantumly hard setting where it can't run on a quantum computer either. You can't train these models efficiently. And this should make us nervous because a lot of work went into developing this idea. But there are some positives that come out of this. And really, it's the moral of the story, unfortunately, again, I don't have time to get into the details, is that because of these results, we should only expect advantages in quantum learning that are polynomial in the system size. So nothing very large, like exponential. And we should only expect these advantages during inference. So in other words, after we've trained the model and we've kind of deployed it on our server or whatever. And then finally, even then, you kind of need some special structural properties to show any kinds of quantum classical separations. So, yeah.
So why in the quantum case, the data what's the high level?
Yeah, so the high-level intuition is that unlike a normal neural network, this is going to get slightly more technical. Yeah, just this picture I've drawn. If you're familiar with these kinds of diagrams, these lines, I guess you can call neurons, are entries of these weight matrices that go into the linear layers of your network. And we directly parameterize each of the entries of these weight matrices. In other words, when we do gradient descent to optimize our loss function, we directly tune each of these parameters. Quantumly, it turns out this isn't efficient because these linear operators are exponentially large. So what we do in the quantum setting is we have like a few parameters, parameterizing this exponentially large matrix. And so, we're in this very different picture where instead of directly controlling each of these wires, it's like a few parameters are kind of controlling all of them at once. And it turns out this feature is what gives the very different training properties. And once you have enough layers where, or enough parameters where you can actually directly control each of these lines, then actually it turns back into the classical picture. But then the issue is you have exponentially many parameters, and so you can't do anything efficiently there. So that's the high-level picture. Yeah. Yeah. The accurate rate? Well, it depends on the problem. And essentially the moral of the story in this line of work is that you shouldn't expect high accuracy in generic quantum neural networks. Generically, you'll get stuck in these terrible local optima and have very bad accuracy in whatever learning problem you're trying to use it for. You really have to have, these papers in the middle look at very structured problems where you can actually prove there are kinds of advantages, but here they're more modest. It's not as large as maybe you would hope naively. Okay, any other questions before I move on to optimization? Okay, so yeah, let's talk about optimization. In particular, let's talk about combinatorial optimization. This is a very computer science topic. And I'm gonna, hopefully there aren't too many complexity theorists in the audience. I'm gonna tell you why complexity theory can actually be very misleading in trying to understand why problems are hard. So to do that, I'm gonna talk about a specific example. I'm gonna tell you about max clique. So if you're not familiar with max clique, here you're given some graph. So here's a graph on 6 vertices, and we're interested in finding the largest clique of this graph, hence max clique. So what a clique is, this is just a complete subgraph. So in other words, for this graph, the largest complete subgraph of it is this 1, 2, 5 kind of cluster over here. Okay? And if you're familiar with complexity theory, this is like one of the standard examples of an NP-hard problem. It actually is even worse than this. There's a famous result in complexity theory known as the PCP theorem. And what it says is that, among other things, this problem is hard to approximate. So for any choice of constant, so I pick some epsilon greater than 0, it turns out it's NP-hard to find a clique achieving an approximation ratio of 1 over n to the 0.999, say. So just to kind of dissect this a little bit more, because I know it's a lot of terminology. If you don't know complexity theory, all I mean by NP-hard is really hard, okay? Hopefully people here know complexity theory, given the computer science audience. But approximation ratio, what I mean here is that the bound value, so the size of the clique that your algorithm outputs, the ratio of that size to the actual max clique value, this is the approximation ratio. And so the reason this is very disheartening is that actually, okay, the size of the largest possible clique is just n, right? If you have an n vertex graph, the maximum size of a clique is n. And you can come up with a really dumb algorithm, which just outputs a single vertex. And already we've achieved an approximation ratio of 1 over n, right? So 1 over n is really easy. 1 over n to the 0.9999 is really, really hard. And it's, it's kind of sad that we can't do better than the trivial algorithm. I mean, we can, it turns out, but up to log factors, you can't do better than the trivial algorithm. Okay. So I'm going to tell you why that's maybe misleading on the complexity of this problem. And the reason is, okay, well, at least often it's the case that complexity theory tells us the hardness of worst case instances of these problems. Like typically complexity theory, the way it works So you do some kind of worst case reduction between problems and complexity classes and use that to argue the hardness of a problem. So it's very much based on the worst case. But you could also ask the question, well, what about for typical inputs of the problem? So for instance, what I could do is sample a graph from what's known as the Erdős-Rényi distribution of graphs. So if you're not familiar with this, all I'm doing is I'm picking whether or not I include a given edge by flipping a coin, and then if it's heads, I keep the edge. If it's tails, I don't have the edge. So it's just some random distribution of graphs, or fixed distribution of random graphs. Anyways, so here, okay, I sampled some graph. You can see what the max clique is. It's just this kind of triangle of vertices. So I won't get into this, but it turns out there's some kind of standard, probability bounds that you can use and show that the value of the max clique over this distribution of graphs is 2 log n. So slightly more technically, you can just use something called the Paley-Ziegman inequality and prove this. And this is already great because this really dumb algorithm I mentioned earlier, where you just output a single vertex, well, if the max clique size is only 2 log n, I'm already achieving 1 over 2 log n. So this is already much better than this 1 over n to the 0.999. Okay? So that should give us a hint that maybe complexity theory is not the right lens to look at the hardness of this problem. Yeah.
And so you mentioned instead of looking at the worst case, we may need to look at the typical cases. But when there's something from a graph, the ER graphs are random graphs, but in our daily life, most graphs are parallel.
Yeah, sure. So this is just a model of this. You could ask the same question, though, for any distribution of graphs that you'd like. You can use kind of similar probability techniques often to show there's some kind of max value that's self-averaging. In other words, like not only is the expected max value some number, but also with high probability, you're kind of close to that max value. And you can run the same kind of argument as I'm doing here. Yeah, but this is a simple example. Okay, any other questions? Okay. Right, so it looks easier than we expected. So let's try and come up with an algorithm for it. And I'm going to tell you about an algorithm from the 70s, actually, by Karp. So 50 years ago, actually. And it's an algorithm for max clique. So what we do is we just pick a random vertex. And then in our graph, we throw away all of the vertices not adjacent to that vertex. So I picked some random vertex. Now I'm going to throw away all the vertices that don't touch that vertex. And I just repeat this process. So now I pick some other random vertex. I throw away some vertices. And at every step, if I have one of these Erdős-Rényi graphs, I expect to throw half of the vertices away at each step, right? If I included an edge with probability of half, roughly at each step, I'm throwing away half the vertices. So this process terminates after log n steps. And so if we go back to what the max clique size was, suddenly we're doing way, way better than what we were seeing earlier. We actually can achieve a constant approximation ratio. So we've gone from like 1 over n to the 0.99 being hard to 1 over log n to now 1/2. Okay. And the natural question is, well, we're beyond the realm of PCP theorem. Can we actually do even better? And if you look at like review articles in this field, they're very hard on themselves. And they'll say, well, it's an embarrassing open problem. After 50 years, we cannot come up with an algorithm that does better than this very simple algorithm that achieves approximation ratio 1/2. So I'll get more into why this is the case later. But more generally, this problem of max clique is an example of what we call a statistical computational gap. So what I mean by that is there's some optimal value that we can compute without doing any work. We just did this kind of statistical technique to say that with high probability, the clique value, max clique value, is 2 log n. But what we can compute is, there's some gap between these two numbers. Okay? And the natural thing to ask now that we have access to quantum computers is, well, what about quantum algorithms? There are kind of two universes we might live in. There's one universe where actually the value achieved by quantum algorithms is better than the value achieved by traditional algorithms. And there are a lot of heuristic algorithms out there kind of thinking about this. And then on the other hand, there's kind of the sad universe where these two numbers are the same. So, okay, what universe do we live in? Well, it turns out we live in the sad universe. I will get into kind of more optimistic results in a second, but at least for the standard kind of combinatorial optimization problems, we live in the sad universe, as I showed in these two papers. More formally, I showed that actually these two values are identical, but showing this unconditionally would make me a Millennium Prize winner. So I didn't show that. What I did show was these two values are the same if you restrict to looking at algorithms that I call stable algorithms. So what do I mean by that? All I mean by stable algorithms are if I have some, say, graph input, for max clique, to my algorithm and it outputs some solution, well, if I change the graph a little bit, so here I've just changed a couple of vertices, a couple of edges, then the output of the algorithm should be roughly the same. So slightly more technically, the algorithm has to be a Lipschitz continuous function of the inputs. Note that this property is kind of independent of what I put here, quantum or classical algorithms. And this is kind of the reason why these two quantities are the same. The value achieved in optimization or in combinatorial optimization for quantum and classical algorithms, if you're looking only at these kinds of Lipschitz continuous algorithms, you do just as well whether or not you're using a quantum or classical algorithm. And for kind of the more experts in the room, this class of algorithms includes things like quantum generalizations of Markov chain Monte Carlo, quantum generalizations of simulated annealing, quantum neural networks, phase estimation, kind of all the standard quantum algorithm primitives we know. And also this includes very recent algorithms, including this algorithm put out by people at Google. It turns out if you have some assumptions on the decoding rate that some hyperparameter that goes into this algorithm, you can also show that these algorithms are unable to do combinatorial optimization beyond what classical algorithms can achieve. So, let me just go through the kind of idea behind this. And to do this, I'm going to get slightly more technical. So I'm going to, I have this graph. I'm going to number the vertices. And I'm going to label subsets of the vertices with bit strings. So just as an example, this kind of red triangle, I'm going to label with this vector, 1 if I have a vertex in the subset, or 0 if I don't. And really what we're interested in is trying to maximize this function of the Hamming weight of this bit string, with some penalty in case it isn't actually a clique. And to show, why this is hard, I'm going to do a kind of funny thing. So I'm going to look at all bit strings that achieve some approximation ratio mu, to this problem. So just as an example of this, if mu is really small, I kind of expect many, many bit strings to achieve this approximation ratio. It's a very low bar to achieve. Also, I should note, this is like these are n-dimensional bit strings. I only have 2 dimensions to work with, so I'm kind of heuristically plotting them out. But you should think of each of these dots as some bit string. Now, if I overshoot the approximation ratio, if it's greater than 1, I shouldn't expect any configurations achieving this approximation ratio. And maybe if it's approximation ratio 1, I have a single solution. But something funny that happens with max clique and other problems is that at these kind of intermediate approximation ratios, I have a kind of clustering property. So it turns out my near optimal solutions are kind of clustered together. And it turns out the approximation ratio this clustering phenomenon kicks in at is exactly this computational number, this computational f-alg that we can achieve efficiently. So to understand why, I'm going to do the following. So I'm going to look at a random graph. I'm going to look at these clusters of solutions. And then I'm going to resample some of these edges. So I look at a single vertex and I just resample whether or not to include these edges in the graph. And I do this kind of repeatedly. Oh, and I should say, right, let's say we have an algorithm that outputs one of these configurations. Well, as I resample these graphs, if my algorithm is achieving a high approximation ratio, it should be outputting one of these configurations. But at some point, if you kind of do the analysis more carefully, it turns out it's going to have to jump from one cluster to another. Kind of because by the time I've resampled all of these edges, it's an independent instance. So these clusters should be uncorrelated with my initial clusters. And because I have this jump, if I have an algorithm that kind of depends in a smooth way on the input to the problem, it can't make this very large jump in Hamming distance. So this is kind of the idea behind why these stable algorithms are unable to optimize combinatorial optimization problems with this kind of structural property. Okay, so that's what happens for combinatorial optimization. But that's kind of an unnatural place to look for use cases for quantum algorithms, given what quantum algorithms are really good at are simulating quantum mechanics. So to introduce this, I'm going to talk about what's known as the ground state problem. And if we think of combinatorial optimization as some maximization problem over bit streams, what the ground state problem is like a quantum generalization of this. Here, I'm interested in trying to find examples of these quantum states that maximize some structured function of these quantum states. And this seems kind of strange, but it actually shows up a lot in chemistry. So often what people are interested in is finding like the lowest energy configuration of electrons in a molecule, for instance. And this is actually a very common benchmark for quantum algorithms, is how well quantum computers are able to do this kind of optimization. So, okay, this topological picture of clusters and reasoning about jumps in algorithms starts to break down now, because now if you view algorithms that are outputting these quantum states, it's not obvious at all what it means for these kinds of strange objects to be clustered. So this is something that I tackle in my work. And I actually make use of a problem that people are often worried about with quantum computers, which is that quantum information is very sensitive. So actually a lot of work in quantum information, quantum computation, goes into correcting errors in quantum computers and things like this. But we're actually going to make use of the fact that quantum information is very sensitive. So what do I mean by that? Well, it turns out if I have a quantum computer with some internal quantum state, if I have a very error-prone quantum computer and maybe it's applying some operations I didn't intend for it to apply, I have some random errors. It turns out some feature of quantum mechanics that this quantum information undergoes a process that we call decoherence. In other words, this quantum information starts to just look like a classical object. It doesn't have these negative quantum mechanical strange features. It becomes really just a classical probability distribution. And one funny feature of this is actually if I recalibrate my quantum computer, or I have some kind of different error model, the classical distribution I get out from this process is different. If I do it again, I recalibrate, I'll get some other distribution. And it turns out these different error channels, this idea has been known for a few years now, these different error channels are revealing what we call classical shadows of the quantum information. So, if I have my quantum state, you can kind of, at a high level, view some error channel being applied to this quantum state, revealing some shadow of this information that's like it doesn't contain all of the information of your quantum state, but it gives you some idea of what's going on in your quantum state. And if I had a different error channel, I would get some other information out. Okay, so these are like classical signatures of your quantum information. And okay, I more generally show for the ground state problem that actually if I can write this optimization problem as a linear combination of optimization problems of these, or linear combination of functions of these classical shadow objects, and this decomposition is small, I can do this kind of efficiently. And also each of these individual functions exhibit this kind of clustering property I mentioned earlier. Then it turns out you can actually show that this more general kind of ground state problem is also average case hard for, once again, stable quantum algorithms, where this includes things like quantum generalizations of MC-MC and annealing, and also phase estimation. And okay, unfortunately for physicists interested in this kind of thing, it includes problems that are actually interesting to physicists. So these bosonic models of holography, if you're interested in kind of high energy physics, you know what this means. If not, it's okay. At any rate, some very interesting quantum models kind of have this property where we want to do some optimization problem, but it turns out it has these structural features that make it hard for quantum algorithms. But okay, so I promised you at the beginning of this talk, when to use quantum algorithms. At this point, you might be a little disheartened because it's more like when not to use quantum algorithms. But let's go back to this kind of philosophy of my research. So we've covered what makes these optimization problems hard. And for instance, one thing that's very important for this problem to be hard is this property. So if I'm interested in finding the ground state, so doing this kind of crazy optimization problem, I really, this hardness result really requires the fact that this decomposition is efficient. But we can consider a specific example that doesn't have this property. So to do this, I'm gonna talk about something called the SYK model. So if I go back to this kind of physical or chemical system that people in drug discovery and so on are interested in optimizing kind of the electronic configuration of these systems. Trying to do this in practice or trying to understand this is very difficult. So we can do what in physics we call coarse graining and essentially assume, well, this system is so small, we can kind of ignore the fact that there's some three-dimensional geometry and kind of consider it like a point-like object. I won't get into the details, but at a high level, this model of electronic systems is known as the SYK model. It's been very influential in physics. And you can view it kind of as a random model of interacting electrons. Okay. So we can model this kind of optimization problem of trying to find the lowest energy electronic configuration of these systems as some kind of optimization of these SYK model-like objects. And we can ask, well, can quantum algorithms do this? And you can show, actually, the answer is yes. So the way to do this, first you can show, actually, that these fermionic systems, or this kind of strange SYK model, if I try to have some kind of decomposition in terms of these classical shadow objects, this R, so the number of terms in this decomposition, is lower bounded. It turns out it grows kind of quadratically in the system size. And it turns out this kind of property means that this previous no-go result I had doesn't apply. That doesn't necessarily mean it's actually quantumly efficient. But now that we know it's not necessarily hard, we can actually think about whether or not quantum algorithms can do this optimization. And it turns out the answer is yes. So we show in these two papers that actually whenever this R, so this decomposition, grows with the system size, that actually quantum algorithms succeed in optimizing this optimization problem to any constant approximation ratio you want. And the quantum algorithm that succeeds in doing this is actually a very funny one, but it's very natural for physicists. And all you do is you kind of simulate what happens when you put this molecule in a fridge, is essentially the way the algorithm works. So maybe from a more computer science perspective, quantum generalizations of simulated annealing, if you're familiar with this optimization algorithm, are what are capable of doing this optimization. So just at a high level to understand why that might be the case, you can kind of look at this clustering picture again. I'm going to be very hand-wavy here, but we can look at what happens at sort of high temperatures or very low approximation ratios for these optimization problems. Turns out many quantum states achieve kind of this very low approximation ratio. And as you lower the temperature, so as you do this kind of simulated annealing procedure, you never get trapped in one of these local optima. So this was, you can show that actually when this R grows with system size, this is the picture. You never get trapped in these local clusters using these quantum simulated annealing algorithms. Right, so it turns out you can actually compute this efficiently, and over the course of the last year or so, this has actually led to a bunch of results looking at various physical systems and actually showing whether or not they're suitable for quantum algorithms versus kind of traditional methods of computation. So, combinatorial optimization might not be a good use case for quantum algorithms, but actually for all of these other models, it seems like quantum algorithms are very helpful in performing these kinds of optimization problems that physicists are interested in. Great. So we live in the good universe when it comes to these more general optimization problems. Yeah.
It's like all the systems you are considering.
It's more like what? Say. Yeah, mean field models. Yeah. Yeah, exactly. So yes. So this is, okay, I'll get into this in just a second. But one kind of corollary of these results is understanding the suitability for quantum algorithms for this optimization really is a function of this R quantity. And this R quantity you can actually efficiently compute using something known as a semi-definite program. So there's some efficient, classical algorithm out there that can efficiently bound this R. And so here, all these results I've laid out have all been kind of pen and paper, analytically looking at the result of this SDP. But in practice, I'm interested in doing this more concretely for real physical systems that people are interested in. So, that leads me into where I want to go from here in my research. And generally, I'm very interested in kind of this high-level picture of looking at problems, trying to understand their complexity, not only for quantum algorithms, but also for kind of more traditional algorithms, and then coming up with algorithms, quantum or classical, in the case that these problems are easy. And so that leads to kind of a spectrum of future questions I'm interested in answering. So more on the application side is my answer to your question, which is trying to understand how quantum algorithms perform on systems of real interest. So like you mentioned, systems of real interest, you can't really analytically get a hold of how easy or hard it should be for real algorithms. But what you can do, it turns out, for understanding quantum algorithms is kind of reduce it to trying to understand this R quantity, which you can do efficiently. Okay, some other things I'm interested in are trying to, just to rattle off a few of these, trying to understand classical lower bounds for this ground state optimization problem that I mentioned earlier, beyond this very fine-tuned, or this very strange SYK model, trying to come up with quantum memories from these difficult instances of optimization problems. It turns out this is related to spin glass physics, which I won't get into. And then finally, trying to come up with quantum algorithms which achieve this kind of optimal approximation ratio. We have a very nice story in classical optimization of what algorithms are kind of the best to use for optimization. It's like things like gradient descent and BFGS. Quantumly, we don't really have as nice a picture, so this is a direction I'm interested in pushing toward. Okay, so with that, I'm right out of time. So just leaving up a reference slide and happy to take questions. Yeah.
I wanted to ask a general question about the impact of noise from the current quantum computation.
Yeah.
How do you think this will be improved in the future with
Yeah.
software improvements or quantum interaction? Thank you.
Okay, the pop-out answer is both, but I really do think it's both. There have been a lot of advancements in error correction, especially using like, for neutral atom systems, like, CU Boulder has a lot of. There really are advancements in these LDPC codes, which have these kind of non-local checks, which might be an issue for superconducting qubits, but are no problem for neutral atom architectures. So kind of developments in error correction. And also, as the hardware gets more and more developed, we get lower and lower noise rates. And right now, we're at a stage where companies like Google are doing error correction experiments where they actually see, as they make their error correcting code bigger and bigger, they're able to get the noise smaller and smaller. So we're kind of at this inflection point of error correction really giving improvements in the performance of the hardware. I think it's just going to get better and better in the future. Yeah. Ooh, okay, fancy. Do I need my sound on, or do you have your sound?
Hello, can you hear me?
Okay.
Hello, hello.
Oh, we can't hear you.
Oh,
He's gonna take that.
Okay.
Sorry.
Any other questions in the meantime? Yeah. Okay. Sampling is, it turns out it's a very similar story to optimization. Probably actually better for quantum algorithms, depending on what you're trying to sample from. But yeah, roughly it's the same story. So like, okay, yeah.
Does having a single if statement in a program potentially break the Lipschitz assumption?
Okay, great question. I mean, you can cook up, okay, I'll say it this way. You can cook up examples of algorithms which don't have this stability property. So the assumption that we're kind of taking on faith is that these stable algorithms are essentially as good as we could do for these kinds of problems for any kind of efficient algorithm that solves them. So obviously that's a leap of faith. In practice though, I cut a table, unfortunately, for time, but it turns out for all of these combinatorial optimization problems that we have these statistical computational gaps, the value predicted by this kind of clustering property is exactly where our efficient algorithms can achieve. So we don't have any algorithms that do better than stable algorithms for these problems. And so it seems like a good model of what's going on. Yeah.
Learning part.
Yeah. What
would happen if the data becomes quantum?
Yeah, so that's
the same, results will hold.
That's a great question. This is something I'm interested in exploring. There are some results that show very large separations. And for instance, if you're trying to learn a quantum state, so you're given one of these, I don't have it here, one of these quantum state objects, and you're interested in learning some property of it, there you can actually show kind of exponential advantages in quantum learning algorithms versus traditional learning algorithms. So there's definitely more room for advantage there. What I mostly talked about here was quantum algorithms for learning classical data. So yeah, there it seems like more.
When we come to optimization, similarly, if we are in an environment that the system is quantum, then classical optimization might not even be able to function, right?
Yeah, so something I kind of glossed over. You might be interested in many more concrete questions about these like ground states. So one thing you might be interested in are expectation values of these ground states. There's more room for classical algorithms to kind of do something. But if you are interested in, for instance, coming up with the ground state, and then you're interested in some late time properties after doing some time evolution. There you need something like a tensor network representation of your ground state. And something I didn't cover here is actually this R quantity also tells you the classical complexity of things like tensor network representations of the ground state.
More specifically, for example, when it comes to reinforcement learning, when the stochastic environment becomes a quantum system, then you think that classical optimization has any room to provide any scientific, reasonable good policies?
So there it depends more on the specifics. So you could imagine, for instance, a quantum system where the environment is acting on it in a way that it's effectively just acting as a large bath. And in this setting, depending on what question you're specifically trying to ask, if you're trying to ask some kind of concrete property of this process, you can often come up with classical algorithms that can do this. But yeah, maybe we can talk more about it afterwards.
Anybody?
Okay, so like back in 2020s, there was a traditional learning model, like it's called CISO. We just put some descriptors of atoms or molecules to it, and that model infer or get the property of the material created by this kind of atoms or molecules. So this is basically infer, but if we switch to kind of quantum learning, and using the quantum algorithm, do you see like it's replacing these kind of old habits?
So
or just using a more efficient way with the same pipeline?
Okay, that's a great question. So there's definitely room for quantum algorithms here, I would say. Really, the fundamental advantage, and what I tried to get through in this talk, is that quantum algorithms are really good at simulating quantum systems. And that's really where we should be looking for kind of large-scale advantages in quantum algorithms. And so something like this, where you're interested in some property of a quantum mechanical system, particularly, it turns out, when dynamics are involved. So if you're interested in some quantum mechanical process of two molecules binding together or something, there I really think there's room for large quantum advantages in terms of quantum algorithms doing stuff that we have no idea how to do right now using efficient, traditional methods.
Yeah, that's great. So I think I had one more question.
Okay.
CS audience.
Yes.
But I want to ask some physical question. So what student you will have small R value?
Yeah, okay, so what R is measuring?
That's right, you have small R value physically, for example.
Yeah, so it's a measure, it's related to that. So what R is measuring it's a measure of frustration in your system induced by quantum uncertainty. So what I mean by that, for something like the SYK model, okay, if you think of what the SYK model is, or any of these models kind of on the right, if you're interested in the ground state problem, you've kind of some sum of terms, right? And there might be some frustration in kind of finding the ground state of the full system, as it's not going to be the ground state of each of these terms individually. Part of that might be just due to the signs. If the signs are like random signs, you're going to be frustrated. But also, if these terms are non-commuting, you're also going to have frustration just due to Heisenberg uncertainty. You can't have a quantum state kind of maximally being, or you can't have an eigenstate of two non-commuting observables. And so that's what R measures. More formally, it's something more specific, but at a physical intuition level, that's what it's looking at.
That's our spirit. Yeah.